Now, next is certain important points regarding the spring pendulum. Time period of spring pendulum is independent of acceleration due to gravity. This is why a clock based on spring pendulum will keep proper time everywhere on the hill or the moon because G is not taken into consideration in a satellite, and time period of spring pendulum will not change inside the liquid if the damping effects are neglected and oscillating mass is completely inside the liquid. So I will just highlight the damping effect. That is, whenever we keep an object in the liquid, we find that if it is vibrating, damping means that during vibration, if the amplitude goes on decreasing, it means damping is caused. And undamped means the vibrations have the same amplitude. So damping effect means that gradually the amplitude reduces and amplitude vanishes. This is what the meaning of damping effect. Now, this is indicated in the given figure, that is K spring constant, and here the spring is indicated in a vertical motion. So mg is the weight suspended with the spring, and we find that x naught, that is, we stretch the spring downward, so the force will be upward. Mean position will be towards the rigid support. So we have written kx naught, and the length of the spring is L plus x naught. Mg is the weight of the body suspended to spring. So here we can take initial length as x naught. If x naught is the change in length on attaching a mass m to vertical spring, then in equilibrium position or at the mean position, kx naught will be equal to mg. Normally we write this equation as ky is equal to mg, but now because our assumption is that there is variation or the change in length is x naught, so we have taken kx naught equals to mg. Now from this equation, we get the value of m over k. M means inertia factor and k is the spring constant. So m over k will be equal to x naught over g. Now in order to find time period, the formula for the oscillatory motion is t is equal to 2 pi under root m by k, and for m over k we compute x naught over g, and our expression will become t is equal to 2 pi m over k, and m over k is written as x naught over g. So the final equation will become t is equal to 2 pi under root x naught g. Here g, as g increases, x naught will proportionately increase. So it means due to increase in g, there is increase in x naught. It is a proportionate change. So x naught over g will remain constant, and hence t will remain constant. So that indicates that g does not affect the position of t. So here g increases means x naught increases in the same proportion, and x naught over g will be constant. So we have written as m over k, and that will be constant. Time period of spring pendulum is proportional to square root of mass suspended. This is what written in the above equation, where we have written 2 pi under root m by k. So t is proportional to under root m. Now when we speak frequency, it is the inverse of time. So n is inversely proportional to square root of m. So we have written n proportional to 1 over root m. Larger is the mass, greater will be the time period. So mass will control the time period. So mass affects the time period, or frequency is also affected by the mass. The time period is inversely proportional to square root of force constant k of the spring. So here we have mentioned in the equation t is equal to 1 over root k, or n is proportional to k. The K spring constant for hard spring is always greater than the spring constant of soft spring. We are very frequently using this term spring constant. It is defined as force per unit displacement. The displacement may be vertical or horizontal. So the unit of spring constant will be Newton per meter, and from that we can also estimate the dimension. So K is F over displacement. So for F, we can put MLT minus 2 divided by displacement L, and we can get the dimensional equation of K. Larger is the force constant, greater will be the frequency, and lesser will be the time period. Now, if the spring has mass M and mass M is suspended from it. Now, spring has got the mass M, another spring, another mass small m is suspended from it. The total mass will become, that is, m plus m. But here we have taken, if the spring has mass m, mass is suspended from it, the effective mass is given by m plus m by 3, so that T is equal to 2 pi m effective divided by K, or T will be equal to 2 pi under root m plus m by 3 whole divided by G. The time period is not affected by G. This has been explained earlier. Now, next thing is, if two masses are there and they are designated by M1 and M2, are connected by spring and made to oscillate on a horizontal surface. Obviously, when it is moving on the horizontal surface, the displacement must be horizontal, so it should be represented by x. Then the reduced mass is given by function 1 over mu is equal to 1 over m1 plus 1 over m2, so that T is equal to 2 pi under root mu over K. The normal equation is time period T is equal to 2 pi under root m over K. So m is replaced by mu. So that's why the dimensions of mu are the same as that of mass. And K is force constant.